It's never easy coming to a foreign land and a new culture and a new language, and even harder when you're trying to pursue something as challenging as a PhD degree. Daijiang Li first wrote to me in 2010, 6 years ago almost now, and said, for application, the most important thing to me is to find a project that interests myself. The ranking of the university, the city where it locates, salary, and other things like that are secondary. The good projects for PhD students is everything. So that struck me, and it's been my wisdom in choosing Daijiang Li as a student for admission and a promising PhD candidate has been amply confirmed in his performance since then. I was next impressed after he came here when he came to see me in his first semester and laid out a plan for his entire PhD, right down to defending his PhD in the spring of 2016. You can see where he's kept to his plan with admirable accuracy, and he's managed to fit into that time not only a PhD in botany in a new culture and a new language, but also a master's in biometry, significantly expanding and enhancing his capacity and the key quantitative skills that he will need to succeed in his career. He came here, however, with excellent preparation. He was a scholarship winner and award winner at his undergraduate years at the university in Yunnan. He also had a master's degree experience at Sun Yat-sen University in China, where he won additional awards. And so, in many ways, his trajectory was set even, I think, in his time in China. He's been a favorite in the Waller lab for how conscientious is it. I was trying to think of words that describe Daijiang Li, and conscientious is one of the best ones because he's methodical, he's careful, not just in planning out his whole PhD, but in considering all the pieces, all the skills he would need to succeed. It was also an early conversation that led to our decision that he would do the pine barrens in Wisconsin, a resurvey with a significant and a challenging field research project, because I didn't want him to focus only on data analysis and interpretation. I considered it essential for a PhD in botany from the University of Wisconsin in plant ecology to really have that field experience too, and that's enriched and informed a lot of his work since then too. So I'm happy to introduce Daijiang Li, who will talk to us about long-term community dynamics in the pine barrens of central Wisconsin, species, functional traits, and phylogeny. Right.
Thank you, Dan. Thanks everyone for coming. I can't believe this is happening. I'm going to talk about my research here over the past 5 years. And today is March 8th, 2016, and it will be a really warm day with minimum temperature to be highest over the past 70 years. Can you believe that? Well, but I wonder how many of us can still remember the weather of last year today? Anyone? Probably not, right? Or maybe some of us can still remember that about 2000 or even 1950. Well, these are easy questions because we can find that answer easily just to looking at the historical temperature record, right? But how about if we ask the same question for plant communities? Imagine there's a small forest near your house, and you want to ask, how did it look like, say, in 1950? Well, this is not a so simple question now, but a step backward. Why should we care about this? Why should we care about how plant community changed over time? Well, this is because we depend on the ecosystem services provided by plant communities, such as fresh air, clean water that we need every day, every minute. So in order to conserve or to manage it, even to restore the plant communities we care about, we need to understand how they respond to climate change or some other environmental changes, and then the answer for the question about how they changed over time will be extremely important for us, especially in the age of global change. And one of the major concerns is of climate change, We know that the past February was the warmest February, and the past year was the hottest year on record. And in fact, 15 of the 16 hottest years occurred after 2000. So 15 out of 16, think about that. And Wisconsin, of course, is not exceptional for such changes in climate. We can see most of the state has experienced warmer temperature, and most of the southern and central Wisconsin has experienced higher precipitation, while part of the northern Wisconsin has experienced lower precipitation. And another major concern is our management in fire. So we know that fire has huge impact on plant communities. For example, fire will keep the understory of communities clean by burning the leaf of stems, nettles, thus accelerate nutrient cycling, and it will also keep the canopy open and will reset succession for plant communities. Some researchers even treat fire as a huge overall for plant communities. However, fire has been extensively suppressed across the world since the beginning of the last century. And here is the annual burn area of the United States. We can see the burn area decreased dramatically since 1930, and it kept low since the late 50s. And then the question I'm interested in is how have plant communities changed over time in response to both climate change and fire suppression? So in order to answer this question, what do we need? Of course, we need some plant communities that suffered from both climate change and fire suppression. And we need to have detailed historical data for these communities, such as, that's the same thing as a temperature record, right, in order to answer this question. The detailed historical data are extremely rare, surprisingly, but fortunately here we have very good detailed baseline data for the vegetation of Wisconsin. Thanks to John Curtis and his colleagues and students in the 1950s, they have sampled over 1,000 sites across the state, and the plant ecology map here carefully archived all the data, which allowing the following researchers to be possible. And this is the exact reason that I came here about 5 years ago, and I'm glad that I made that decision. And for my dissertation, I focused on the pine barrens of central Wisconsin. According to the definition of John Curtis, pine barrens is a fire-maintained ecosystem with jack pine and northern pine oak to be dominant trees, and with less than half of their canopy open. And the pine barrens in central Wisconsin have very sandy and nutrient-poor soil, and that's part of the reason that fire was very common before extensive fire suppression. And in 1958, James Tobacco reexamined 40 such communities, even though he called them the upland forests. But according to the definition of John Curtis, most of these sites can also be called as pine barrens. And therefore, we will refer these communities in 1958 as pine barrens. Jim got his PhD here in 1959 and then moved to University of Montana as a professor there, and he's still actively involved with research and outreach nowadays. So we can see Jim here in 1955 and 2014. Was age 82, he's still, pretty good.
That's Bruce McEwen and Pat Muir.
Yeah. And this one, I think, is Bob, is one of the PhD students of Grant Carlton here. So Jim sampled this community in 1958 used the so-called point-to-plant method. So imagine that you get to a forest, then you randomly select a point, and you divide the area near you into 4 quarters. Then you find the closest tree from the quarter to the point. And then you record the tray, you measure the tray, and examine 20 points at each site. This gives us about 80 individual trays and saplings. And at each point, we also use a 1 meter by 1 meter project to look at the understory, the presence and absence of all vascular flora within that project. And in addition, he used a densirometer to measure the canopy cover of each site. So in 2012, we re-sampled 30 out of 40 such sites and use slightly different methods. This method has been demonstrated to be more efficient in the distribution of sampling effort and also has more power in detecting rare species. Briefly, we used the 5 parallel 50 meters long transects, and on each transect we then put 10 1 square meter projects for the understory, and we used the first, the third, and the fifth transects to sample the overstory, such as trays and saplings. And we used the fisheye camera to measure the canopy because I can't find the densirometer. And I think the fisheye will be more efficient, and you can keep the record there. So in a previous study that compared these two methods demonstrate that these two methods provide very comparable results about the estimation of the canopy shape. So we can see most of the resurveyed sites were located within the tension zone of Wisconsin. The tension zone, although it was defined by John Curtis by the distribution of species, their boundary of a range, and but it also reflects rapid climate change over this area, and therefore we can expect that communities within this area to be very sensitive to changes in climate. So as a result, we think these communities will provide us a very excellent opportunity to study the long-term effects of climate change on plant communities at a relatively small scale. In addition, based on the information I got by talking with landowners or DNR, now this site has been burned since the 1930s. So therefore, this used to be maintained by fire pine barrens will also be an excellent system to study the long-term effects of fire suppression on plant communities. But wait a minute, what do we talk about when you say community? Traditionally, ecologists just think community as a connection of species. So we only care about, say, how many species we observed in this site and what are they. So basically, we focus on the species name and their abundance. However, for example, for these 3 species, imagine like if we don't know anything about this community, these 3 species, can you imagine how tall they are, or how large their leaves are? Well, we have no idea. But so that's one of the reasons that we ecologists move on to measure the functional traits of plants directly. Functional traits are defined as a characteristic of plants that are physiological, morphological, morphological, or phenological that will affect their, say, growth and fitness. For example, we can measure the height of the plant, and we can measure the leaf area of the plant, or say the carbon nitrogen content of the leaves, and there are so many of them. Because the function traits provide us a mechanistic link between species composition and ecosystem function, and it gains more and more attention now. However, a limitation for such methods is that there are so many function traits, and it's just impossible to measure all of them simply because we're limited by time, limited by budget, and therefore we use phylogeny as a proxy for functional traits, assuming that closely related species will be similar in their functional traits also. So by looking at the phylogenetic relationship of species within the community, we can study what's the phylogenetic diversity of the community, or we can test whether closely related species are tend to co-occur at the same site more or less than expected by chance. There are many questions we can ask from each of these perspectives about communities. And these are the three most perspectives about plant communities. And I will use all of them to look at the changes of pine barrens in central Wisconsin. So the first question I asked is, how has the species composition changed over time in these communities? Specifically, we first look at the overstory, and we expect the successional changes in this overstory because of fire suppression, and we expect that the mid to late successional trees, for example, white pine, will replace the dormant tree of pine barrens such as jack pine and northern pin oak. And we then look at the understory. Based on previous study about fire and plant communities, we expected that we will observe decreases in local species diversity, that is the species within each site, species diversity within each site. And because of fire suppression, and we expect the sites to be more similar with each other in their environmental condition, say their canopy closed, and so we expect they also to be more similar with each other in species composition, and that will lead to decreases in regional beta species diversity. That's a species diversity across sites. And we also expect the successional changes, that is, shade-tolerant species will replace, say, fire-adapted or shade-intolerant species. For possible drivers, we think both climate change and canopy shade will be main possible drivers for those changes. So across this talk, I will use these three phrases exchangeably. Decreases in beta diversity will mean increases in site similarity and homogenization. So we first looking at the changes in environmental conditions of these communities. We can see the canopy shade increased dramatically over time. In 1958, most of the sites are below half of the canopy shade, and with the median to be 55%. But in 2012, the median is 88%. So that's dramatic changes. And we also observed higher average temperature for these communities. And the average temperature increased about 0.7 Celsius degree, and even more for the minimum temperature of these communities. We observed that the average precipitation of these communities had increased about 72 millimeters over this past 54 years. And consequently, we can see the effects of canopy shade and the community decreased significantly over time. Although the precipitation and the minimum temperature, their effect doesn't change too much. Here's a typical view of the communities in 2012. We can see most of the down or lean trees were jack pine, with this one to be northern pin oak. And most of the new saplings, they were white pine with red maple distributed across the lower canopy. And so this again suggests that our successional changes expectation is correct. And we then look at the changes in the overstory importance values. Importance values is a measure of species relative frequency, their abundance, and basal area across all sites. So it is a measure of about how dormant or how important they are. And we can see the dormant species of jack pine and northern pin oak of pine barrens, both of them decreased a lot. Well, the white pine, red maple, and red pine have increased in their importance value. Again, this suggests the successional changes in the overstory is happening. And we then look at the understory local species diversity. Surprisingly, we observed that the species diversity increased over time, with the only exception is for species richness, which has decreased. And we think that the opposite result of most previous studies, because we have longer time period for our study. So if we think in the beginning, just after fire suppression, the species diversity will decrease, but with time, then the species will increase because you get more species immigrate from other communities, or you get more, say, shade-tolerant species. And so also the increases in woody, fern, and granuloid species richness again suggests successional changes in those communities. And we then look at the species composition of those communities. So each triangle here would represent a site in 1958, and each dot represents a site in 2012. We can see all the dots are more close with each other in 2012. That suggests that the species composition of these communities are much more similar with each other in 2012 compared with those in 1958. And importantly, the direction of the changes in species composition of most sites is the same way as the changes in the canopy shade. This may suggest that canopy shade is a potential important driver for such changes in species composition. And then we then use the regression to test this idea, and indeed, the changes in canopy shade was one of the most significant predictor for homogenization. And another important one were increases in native species diversity, and surprisingly, no climatic variable turns out to be significant for the homogenization process. And we then look at the individual species of understory. We look at the changes in abundance over time. If the abundance of species increased significantly, then we call it as a winner. And if its abundance decreased significantly over time, we call it as a loser. So, as expected, most of the losers were either fire-adapted or shade-intolerant species, and most of the winners are shade-tolerant species. We then use functional traits to ask what kind of functional traits can predict whether a species is a winner or loser over time. And 3 functional traits turns out to be significant. And the first one is the growth habit. We can see most of the losers were forbs, and half of the winners are woody plants. And another important driver for this is pollination mode. We can see all the losers were biotically pollinated, while half of the winners were abiotically pollinated. And not surprisingly, shade tolerant also turns out to be important. We can see most of the losers to be shade intolerant, and about half of the winners are shade tolerant species. So to summarize about this question, we have observed increase in local species diversity, but decrease in regional species diversity, suggests that these communities are much more similar with each other now in their species composition. And possible drivers for such process is succession and also increases in native species. This result suggests that fire suppression has driven these communities, these used to be pine-based communities, into close canopy upland forests now. We then move on to ask how has the functional composition changed over time. And for the questions, we first asked how has the understory changed in their functional traits. And for this project, we only focus on understory because the understory has much more species than the overstory in these communities. And we expect the increases in shape-adapted traits such as higher seed mass or large and thinner leaves. And we also asked how has the functional diversity changed over time. We expect that the changes in functional diversity will follow the changes of species diversity. That is, you observed more functional diversity within each site, but all sites are getting more similar with each other in their functional composition. And for possible drivers, again, we think canopy shade and climate change will be important. For this project, we used the 9 functional traits. The first 3 were derived from the winners and the losers analysis that turns out to be important. And then we also added 6 numeric continuous traits. And SLA is leaf area divided by the dry mass. So in a shady or mid understory community, you expect the species to have larger SLA. So larger leaf, thinner leaf, but like more less dry mass. So we first look at the changes in community weighted mean. The community weighted mean is the average value for the traits you studied weighted by species abundance of that within that site. We can see the first 3 traits give us pretty much the same results about the winners and the losers. We can see we observed more woody and shade-torn species, but less biotically pollinated species. And we also observed for the species in 2012 to have larger SLA, to be taller, and have larger seed mass. And all these first 6 traits have changed significantly, but the remaining 3, that is leaf nitrogen content and stem dry mass and leaf carbon content, they didn't change significantly over time. So we then can observe the functional diversity. As expected, the changes in functional diversity has the same pattern as those in species diversity. That is, we observed higher alpha diversity and lower beta diversity. However, we know that functional diversity usually correlated with species diversity. So in order to look at the pure functional diversity, we should factor out the effects of species diversity. And to do this, we use no models. For example, when we get the site by species matrix with the abundance of cells, and we also get a species by trait matrix, that's the trait value for each species. Combine these 2, we can calculate or observe the functional diversity for each site. And then we reshuffle the species name within the second matrix, but keep the first matrix intact. This will break the relationships between species and their functional traits, but keep the species composition intact. So by doing this, we can calculate the expected functional diversity for each site. And by reshuffling this 1,000 times, we can calculate the distribution for the functional diversity we expected, given the species composition of the pulse at each site. And we can then look at the standard effect size of the observed function diversity using this formula. And if the SES is less than 0, we can get 1 SES for each site. So 30 of them, we got 30 of them. So if the average SES is less than 0, we conclude that the value we measured is significantly less than expected by the given species composition. And if it's higher than 0, then that's opposite. And for the alpha function diversity, after factoring out the species diversity, we still observe the higher function diversity. And for beta diversity, we observe the lower function diversity. So again, the changes in function diversity is in the same direction of those changes in species diversity. We then look at the possible effects of changes in climate and changes in canopy shape on these changes in alpha and beta function diversity. It turns out that changes in climate and canopy shape interactively affected alpha function diversity, but not beta diversity. So with the canopy shape, the change of canopy shape is small, then we can see the positive relationship between climate change and the changes in alpha function diversity. But when the canopy shape, the change is large, then it turns to negative. So this suggests that even though now we observed higher function diversity in 2012, but the future function diversity will likely decrease with continuous succession and climate change. So to summarize, we observed that the changes in function diversity is the same as those changes in species diversity, increase in local function diversity, and decrease in regional function diversity. And canopy cover interacted with climate change to affect the alpha function diversity, and this suggests a future diversity in these communities may well decrease. So next, instead of looking at the changes in phylogenetic composition, we look at both methods. Say we ask whether the information derived from functional traits methods overlapped with those from phylogenetic information. So because both methods has gained more and more attention, very few studies has explicitly to test whether these two methods give us similar or different information. And most previous studies, use these two methods separately, and if the information they contain are different and overlap very few, then maybe we should put them together in the same study. So imagine that we have the species abundance for species across communities, and then we have the phylogeny for the species. We can use the phylogeny to explain or even to predict the abundance of species, assuming that phylogeny will be a good proxy for the functional traits. And of course, there are other variables that we didn't count here for the abundance of species. And statistically, this is we can use a model to estimate the parameters for the phylogeny term. And if we have measured traits, then we can use the traits directly to explain the local community. But the traits will also be affected by the phylogeny and other variables we didn't count. And so we can just add the measured traits in the model. And in theory, if we get all traits measured, then we think the phylogeny will only provide a very small additional, very little additional information about the community. That is to say, the parameter for the phylogeny term in the model will decrease to about 0. So visually, this is to say, if we got all traits measured, then it should already include the information from the phylogeny. However, in reality, we only get a small subset of traits measured. So now, the question about whether the measured traits we have contain the information of phylogeny or not is not answered. And if we define the overlapping between the measured traits and the phylogeny to be A, and the remaining information in the phylogeny about the community to B, then the question we ask is, what's the proportion of A divided by A plus B with the measured traits you have? And recall the previous two models, and the first one, the term of phylogeny will give us an estimation about A plus B, and the second model, the phylogeny term, will give us an estimation of B. So by looking at these two models, we can get an answer for this proportion. But before answering this, of course, we asked, is there any phylogenetic pattern there? And we assume that we will observe phylogenetic attraction, that is, closely related species will be more likely to co-occur in the same site. And I can explain that later. And for this project, we only focused on the community of 2012 and only focused on the common species. So we removed the species that are observed in Madison to 3 sites. Yeah. The community of 1958 gave us very similar results. So that's one of the reasons that we only focus on the 2012 data. So we do not expect the measured traits can explain all the phylogenetic pattern there because we missed some important unmeasured traits. So phylogenetic attraction, that is say the closely related species, they tend to be observed in the same site, while the opposite is phylogenetic repulsion, that is the closely related species are less likely to be observed in the same site. So if we expect the phylogenetic attraction, then we should expect some horizontal band in this finger. So this is species in another phylogeny, and these are the sites, and the dots are their local abundance, and their size are proportional to their local abundance. So if we expect the phylogenetic attraction, then the closely related species, they should have similar pattern across all sites. So that's why we should expect some horizontal band. And we can get some evidence here, but we are not sure. And therefore, we use a phylogenetic mini-mixed model. That's the first model we mentioned in the previous slides to test this. And indeed, we find very strong evidence for phylogenetic attraction in these communities. And we then look at the overlapping of information derived from those phylogeny and traits. And with abundance data, the measured traits overlapped with phylogeny about 57%. For the presence and absence, it's about 89%. So in our case, if you just interested with presence and absence, maybe exclude the phylogeny will be enough, but not for the abundance. And why is this? And we think because most of our sites close with each other, so large-scale biogeographic process were likely to be have small effects. So we think the main possible reason is we missed some important traits. But what kind of traits are there? There are so many of them. In order to get some directions, we can look at the responses of species in their abundance to environmental variables. If closely related species respond to the environmental variables similarly, that is, we have phylogenetic signal of the coefficients of slopes, then there should be some functional traits related to this environmental variable that are important for species to adapt to this environmental variable. And with abundance data, even though we observed that species respond differently to most of the environmental variable we tested, but none of them show phylogenetic signal in there, so we can't get direction about possible traits. But for the presence-absence data, 4 of them turned out to be important. We 3 of them to the soil properties, and another one is the minimum temperature. So this may suggest that we missed some traits such as a frost tolerant that will allow species to adapt to lower temperature, or some functional traits for plant roots that will adapt species their ability to uptaking or absorbing water or nutrient from soil, and some such kind of traits maybe will be important to measure for future studies in this community. So to summarize, we find that the sites in 2012 of plant barrens to be phylogenetically attractive, and measured function traits only explain about half of the phylogenetic pattern we observe. So therefore, for plant ecology, community ecology analysis, we should include both phylogenetic information and trace information. So putting it together, we looking at the mountain chains of pine barrens according to the three most common perspectives, and we have demonstrated that the pine barrens have succeeded into upland forest without fire, and we observed increasing of our diversity and a decrease in vapor diversity. That is to say, even though within each individual site, we observe the higher both species and function diversity, but across the region, they are getting so similar with each other. So the regional diversity has decreased. And canopy shade and climate change turns out to be important for such changes. And also, for community analysis, we probably should put those phylogeny and traits in the same analysis. And our results also provide insights to anticipate future possible changes in such community. For example, maybe the function diversity or species diversity will decrease with continuous succession and climate change. Ooh. That's most of that, but I'm also happy to announce that I will move to University of Florida in the summer for a postdoc position there. And of course, all of this won't happen without the support and help with so many people. So especially the funding source first, and research and graduate school and ESA support my scientific communication for ESA meeting, and the Department of Botany, of course, support both. And I especially want to thank my main advisor, Dan, for inviting me here 5 years ago and to allow me to pursue the questions that I'm interested in and to be very supportive across the past 5 years. So thank you, Dan. I really appreciate that. And also I want to thank my committee. I especially want to thank Tony to be practically my second advisor. And I want to thank Adam for encouraging me across the past 5 years in both science and in life. I want to thank Tom for introducing me the beautiful vegetation of Wisconsin and all the movie nights there. I want to thank Brad to teaching me and advising me on statistics, and especially introduced me the biometric master degree. And talking about the master degree, I also want to thank my committee for the master degree. So all the communities gave me very helpful comments and suggestions over the past 5 years. And this will reflect all of your works. So thank you. And I wanted to thank my fieldwork assistants, especially Mariam, shown here. She helped me announce all the research work. And I also wanted to thank Bia, who is not here today. And I want to thank Pat for helpless plant identification. I really appreciate that. And I also want to thank lots of our undergraduate students for their help with functional traits connection and need carbon nitrogen measurement. Of course, I want to thank the awesome Water Lab. You guys are amazing, and it gave me so many useful, helpful feedback in both science and in daily life. I can't even believe that I would stay here without you guys. I want to thank the Daijiang and IVE snap groups to allow me invade their lab meetings. I've learned tons of things from each of them. Of course, I want to thank fellow graduate students, faculty members, and office staffs from both botany and zoology. And especially I want to thank Carl to be here. I didn't expect you came. And thanks for teaching me all the reproducible research tools and methods. That's very, very helpful, and I can't believe I can do anything without them now. And most importantly, I want to thank my family, especially my wife. Oh, they're here actually. Yeah, she came with me 5 years ago, you know. Wow, that's quite much.
I'm sure Daijiang would be happy to answer any questions you might have.
Yeah, I'm ready. Yeah.
Some of Ben's other students in different forest types found that same change in the biotic versus abiotic pollination and attributed it to deer. What do you attribute it to?
I think deer. Yes, deer definitely is one of the main reasons, but I also think the close canopy will be another important factor. So imagine with the close canopy, maybe the movement of the say insects, they are not so frequent or so common in the open area. So I think that may be another possible reason. Yeah.
So the extent to which you see phylogenetic attraction obviously depends on the scale of a phylogenetic tree. If you have a tree of all of life, you'll always see attraction. So I'm just curious, like, how did you decide on the background tree that you would use as a basis for deciding if there was attraction or repulsion?
That's an excellent question, and there are a couple of studies to look at the effects of scale on the phylogenetic pattern. And for my project, I just use the tree that include all the species observed in these communities. So I only use the regional pool of the species, not say the all species including the Wisconsin species. No. Yeah, of course, like using a tree of Wisconsin, we'll definitely find attraction there. But even with a smaller tree, we still find attraction here. So.
In your first chapter, you showed an increase in the gramineals, the grasses and the sedges, right? But in the phylogeny, you included a single tip for grasses and sedges. If you were to use every species as a tip, how would that essentially impact your results?
So for the sedges, graminoids, so we lumped all the carox into carox SPP, and I believe most of the carox in 2012 were Carox pennsylvanica. And if we say split that, then maybe the attraction will be not so strong. But I believe we will still observe phylogenetic attraction because given in 2012 most of the sedges are actually pen sedges. So yeah, that's an excellent question. Yeah, Carl.
With the fisheye lens to measure canopy, is there some trick for adjusting for the change in the stretching of space?
Not really. We just like trying to be consistent. Across all sides, say set it as 1 meter high and to be horizontal, and we measured say 6 of them to get the average to partly account for that. So no, I don't. Yeah.
I've lost another question
Yeah,
then.
sure.
So a different thing. You said at the beginning something about how you did use a different sampling strategy to avoid missing rare species. Well, it was less prone to missing rare species, I thought. Maybe I misheard you. You didn't use a point quarter centered method.
Uh-huh.
You used a different method
Yes.
that was better at picking up rare species.
primarily 50 instead of 20
Yeah.
one way square meter quadrant, so 3.5 times.
Okay.
Yeah, so it's just like a more sampling after itself.
Okay.
So because that will affect the estimate of the species diversity.
Okay, open
And-
off.
Yeah, so we, for the first project, we randomly select 20 projects out of 50 and do this 1,000 times to get an average. So trying to account for the differences in sampling effort. That's an excellent point.
Thank you.
Great, if there are no more questions, please stay around a few minutes to congratulate John and share some more food. The committee itself will be retiring to, do we go to 3:45 or stay here?
I think it will stay here.
Okay,
So
we'll kick you out after 5 minutes.